I can draw it in one stroke like this, right? So it's not really, it doesn't have much value to say that, well, how many corners it has. It's not going to matter for us in the end. When we calculate integrals over a curve like this, of course, we will do it as a sum of integrals over each of the smooth parts. But that's sort of a calculational matter. It's a technical issue. It's not an issue. It's not a fundamental, theoretical issue. The theoretical issue is that the boundary of this domain is this curve, this closed curve. A boundary of a domain like this on the plane cannot consist of a single curve like this, which has a boundary of its own. In other words, boundary of boundary is empty, if you know what I mean. Boundary, if you take boundary of something, and then you take a boundary again, this is empty. I'll use the standard sign notation for empty. Empty. A boundary can be non-empty. This curve has a boundary of its own, but then it itself cannot appear as a boundary of a two-dimensional domain. If a curve appears as a boundary of a two-dimensional domain, it has to be closed. Its own boundary should be empty. You see what I mean? Are there any questions about this? Yes. It should be, that's right. So here's the question is, how does this apply to Green's theorem? Well, here's how it applies to Green's theorem. In the case of Green's theorem, the curve I have is a boundary of something. So this principle, which I explained, boundary of a boundary is empty, means that this one will have empty boundary, will have no boundary. So that means that in Green's theorem, I will, on the right-hand side, I will always integrate over closed curves. You see what I mean? Yes? No, we could apply Green's theorem to this one as well. Let's look at this example. Let's suppose that my domain here is a square. So this is my domain. I can apply Green's theorem to this domain, but then on the right-hand side, let me use a Zen chalk. On the right-hand side, I will have the square as my boundary. Okay? This boundary is slightly different than the boundary in the previous example in the sense that it's a curve which has corners. But it is a curve, and it is a closed curve. This curve does not have any endpoints. You see, this is a closed curve. Closed curve. Empty boundary. This points, it has the special points. I grant you that. It has some special points which are different from the rest because these are the singular points, so to speak. They are not smooth. But these are not boundary points. This is not a boundary. It's in the middle, right? If I had something like this, those would be boundary points, right? But this is still not a boundary point. If I have something like this, these are the boundary points. You have a question? It's empty. It's not. No, this is not the definition of a closed curve. This is a general principle, which is that if I start with a two-dimensional object and take its boundary, and then take the boundary of that boundary, this will be empty. This is illustrated here. I start with a two-dimensional domain. I take its boundary. I get a curve which already has no boundary. Bless you. I know it's a little confusing, so I'll just let this sink in, as they say, you know. And this is an important point. This is an important distinction. So from this point of view, Green's theorem can be, if you have a line integral and you would like to use Green's theorem to understand that integral, you have to make sure that you're integrating over a closed curve. In Green's theorem, on the right-hand side, you will never have a curve like this, or like this, or like this. You see what I mean? You will never have a curve which has boundary, because the curve in Green's theorem is not an independent object. It is a boundary of something on the left-hand side. And because it is a boundary of something on the left-hand side, it has no boundary of its own. Yes? What's wrong with integrating over an infinite two-dimensional domain? What's wrong is that the integral may diverge, right? It might actually be infinite. It may not be well defined. If we integrate over a bounded domain like this, which sort of doesn't go off to infinity, we are assured that if our function is defined everywhere on this domain, we are assured to get a finite answer. Whereas if we integrate over something infinite, we are not assured of that. For instance, take function 1. If you take function 1, then the integral over any domain is going to be just the area of that domain. If the domain is bounded, the area is finite. If it's not bounded, it's infinite, so it's not well defined. But it could be well defined. That's right. It could be well defined, and so oftentimes we are forced to consider integrals over infinite domains. And the way we do it is quite obvious. We approximate the infinite domain by bigger and bigger finite domains, right? And then we integrate over those finite domains and we take a limit. And you're familiar with the notion of limit, so you see roughly how it would have to be defined. But we are not assured in general that the limit will exist, and so the integral will be well defined. Here we don't want to deal with these issues. So from the beginning, we restrict ourselves to domains like this, which are finite. Any other questions? Yes.
So if you have two curves that connect, two different curves that connect, there is no boundary. These connect themselves.
Okay. Let's talk about this. So the question is, suppose you have two curves which connect. How do we calculate the boundary of the sum of these two curves, so to speak, right? So, for example, let's suppose that we have a curve like this, right? So, what is the boundary of this curve? Just from what I said, just from the intuitive description of what boundary means, you can see that it's going to be this, and depending on what the orientation is. Let me put the orientation like this. So, the boundary is this minus this. So that's the boundary of this total curve. Let's call these points. I want to call it ABC, but I don't want to do that because I have C for this, right? So let me call them alpha, beta, and gamma. I think as long as it's not epsilon and delta, you're fine with it, right? So the boundary of C is gamma minus alpha. Right? But on the other hand, you can think of this curve C as the sum of this curve and this curve. So it's what? Let me just do it. I mean, they're not shifted, it's just two different sheets of paper. Right? I can think of this curve as the sum of this one and this one. So let me see, what will I get if I treat it like this? It will be C1 and C2. The boundary of C1 would be beta minus alpha, right? And the boundary of C2 would be gamma minus beta. Right? So if I take the sum, the boundary of C1 plus C2 is going to be beta minus alpha plus gamma minus beta. So you see betas cancel out, and I get the same result. So it's all consistent. The boundary of this curve is gamma minus alpha, no matter how you look at it. You look at it as just boundary of this curve, or you look at it as the boundary of the sum of these two curves. Because the point is that you have to keep track of the signs. If you keep track of the signs, actually this comes with minus, this comes with plus, this comes with minus, this comes with plus, and so these two guys annihilate each other. They kill each other. So they disappear. Does this answer your question? Okay. All right. So let's move on and let's talk more about this Green's formula. Okay, now that we have figured out more or less what the meaning of the boundary is and what kind of curves we can get on the boundary of a two-dimensional region, let's talk about this very strange looking expression that we integrate on the left hand side. So on the left hand side, again, we are integrating this dq dx minus dp dy. And I kind of want to write it as dx dy. This is what we call dA. This is what we call dA when we talk about double integrals. I'm just rewriting the formula, but it's just a slightly different way. I want to focus now on the integrands, on the algebraic objects. We have discussed the geometric objects. Now let's discuss the algebraic objects. So in what sense is this a derivative? Why should we think that this is a derivative? So let me give you kind of an intuitive explanation of this. But let's do it again by analogy with the one-dimensional case. In the one-dimensional case, we were integrating the function on one side, and we were integrating its gradient on the other side, right? So in the one-dimensional case, this is a two-dimensional case. And the one-dimensional case, again, I just want to put them next to each other, is nabla f dr equals, well, let's write it like this, f of b minus f of a. But what is nabla f dot dr? We can write it in coordinates. It is dp dx dx plus dq dy dy. That's what we call nabla f dot dr, right? So you see, this is a derivative. This is what we call the derivative. And in fact, if you look at this formula, what do you see? What do you recognize? Sorry? I should change signs. No, I shouldn't. Here I have the sign. But these are two different formulas, right? Why do you think that I should change sign? Nabla f is a vector field which has two components, dp dx I plus dq dyj, right? When I take line integral of this vector field, I have to take the first component, multiply by dx, the second component multiply by dy. That's what I integrate. But my question is, have you ever seen an expression like this before? In season 2, it made its appearance, right? You know the answer. What is it? Somebody say it. Differential. Thank you. Yeah. So this is a differential. So in fact, this is df. This is df, the differential of f. So you can think that you are doing a line integral of the gradient of the function. But actually, a better way to think about it is the integral of the differential. The differential is an example of what mathematicians call differential forms. And you see that every time we differentiate, we have to have some d's, dx, or dy here. Only one because we're doing a single integral. Or dx, dy, both of them because we're doing double integral. And sometimes we have dx, dy, dz, right? So these objects, all those objects, are mathematically called differential forms. And actually, a slightly more consistent theory of integration can be developed in which the objects that we integrate are differential forms. We take a slightly different point of view, which, because we want to think about these integrals more in terms of applications like work done by force and other things like a flux of a vector field that we'll talk about later. And this is the reason why we are thinking about integrating vector fields rather than differential forms. But algebraically, it's easier to think of this as integrating this differential form, which is just the differential of the function. So in the one-dimensional case, in the case of the fundamental theorem for line integrals, what we are doing, passing from the right-hand side, where we have a function, right-hand side we have a function, and on the left-hand side we have this, what I call the derivative. This derivative actually is just the differential of f. You can think of integrating just the differential of this function. Yes. Shouldn't be a derivative of what? I'm sorry, that's right. I made a mistake. I'm sorry. It's df. That's right. Sorry. And that's why you didn't answer. That's why you didn't answer my question. Sorry, it was my fault. Yeah, I got carried away with all this df, dp, and df myself. Yes. Of course, there's no p and q in this formula, right? P and q shows up here because we have p and q here. Here, there's just what we're given is just the function f, and what I should have written is just the derivative of f in both cases, right? Okay, now it's much better. Do you see now what I mean? Okay, is it better? Okay. So what did we do to get this formula from f? What did we do? We took the function f, and we took two possible derivatives of f, with respect to x and with respect to y, right? So we took f, and we replaced it by df dx plus df dy dy, right? So what is this operation? I differentiate, I take partial derivative, and at the same time multiply by dx, x partial derivative, and multiply by dx, plus y partial derivative, and multiply by dy. That's what it is. Right? So there are two possible partial derivatives. I take partial derivative multiplied by dx, take second partial derivative multiplied by dy. So let's take this as a guiding principle. Now I would like to apply it here. So now my starting point will be p dx plus q dy. And I want to see what I can get from this by applying the same idea, the same procedure. Okay? So let me start with the first term, p dx. When I start with p dx, I apply the same rule. So I take the derivative of p with respect to x, and I multiply by dx. And I keep the old dx, which I had before. Right? So I just treat it like this. I apply my differential to p, but I keep this extra factor as well. So I get this term plus dp dy, and then I have dy dx. Now, have you ever seen dx dx? No. And for a very good reason, right? Because we see dx dy because this represents the area of an elementary parallelogram with sides delta x delta y. The area is delta x delta y. And this is what eventually gives us this term dx dy, which we call dA, in the double integral. But delta x makes no sense, right? Delta x does not represent any area whatsoever. To get an area, you have to have increments in two transversal coordinates, like x and y, or maybe r and theta if you switch to polar coordinates if you like, okay? Or dx, dy, dz if you're doing triple integrals. But delta x makes no sense, and neither does this. So whenever you have dx, this just is prohibited. So you have to cross it out. Or more properly, you should say it is equal to 0. It's like, well, it sort of represents the area of the segment, which is 0. Right? To have an area, you have to have something two-dimensional. Now, this on the other hand is fine. It's dy dx. The only problem is that we switch the order in which we normally take the area, which is usually dx dy. So the rule, in fact, is that this should be replaced by minus dp dy dx dy. This is an issue of orientation. Remember, we talked about different types of orientation, and we know that when we talked about general changes of coordinates under double integrals, we saw that if you switch to coordinates, the Jacobian that you get under the integral gets a minus sign. We kind of skirted that issue by saying, well, we'll just take the absolute value of the Jacobian. But at this point, actually, we can't avoid this issue, and the correct solution to this issue is to say that dy dx is equal to minus negative dx dy. So when we apply this procedure to p dx, this is what we get. But I also have the second term, q dy. So let me calculate what I get for q dy. For q dy, I get dq dx dx dy. This is good. First of all, there are two different variables, and second of all, they are already in the right order. I do nothing. Then I also have dq dy dy dy. Again, I got dy dy. It makes no sense. Cross it out. Okay? You see what I'm doing, right? I'm just taking q, and q gives me this plus this. But I also have the second factor dy, which I keep. And it is the second factor which tells me that the second term should disappear. So let me collect all the terms that I got. If I start with p dx plus q dy, I end up with minus dp dy plus dq dx dx dy. You see? And that's exactly the formula that I get on the left. Well, I write it as dq dx minus dp dy, but I just switched the order. Yes? So the rule is, the quantity function that you have, each of the functions that you have, you should take partial with respect to x and multiply by dx, plus partial with respect to y, multiply by dy. Right? So here is how it works for this term. For this term, I take partial with respect to x and multiply by dx. But don't forget I had dx from the beginning also. So I just keep it, right? Plus partial with respect to y, multiply by dy, and keep the dx. That's what I have. But in addition, I have this term. For this term, I get this answer. So I get a priori 4 terms. But out of these 4 terms, only 2 are non-zero. This one and this one. I put them together and I get this answer. And that's exactly the answer which Green's theorem tells me I should put here. So this is the explanation of this expression. This expression, at first glance, looks unnatural. But now I have shown that you can obtain it in exactly the same way as the expression for the differential of a function, which certainly is quite natural. You know that the differential of a function is actually very meaningful. Okay? Yes? That's right. So this is a subtle point. The question is, why do I put the minus sign? This is a subtle point. Because when we did double integrals, we actually kind of swept this under the rug. Because when we oftentimes would write dx dy, and oftentimes we would also write dy dx, depending on which order of integration we choose, right? Because what we did, we represented double integrals as iterated integrals. We would first integrate over x and then over y, or first over y and then over x, right? Depending on that, we would just write dx dy or dy dx. But in fact, the correct meaning of this expression should involve also the choice of orientation. And the orientation, if you do that, the dA, the measure of integration for double integrals should really be dx dy, and dy dx should be minus that. The reason why we didn't do it, because essentially we were actually always integrating with respect to the same measure. Just the fact that we do the integral in one order or the other order does not change, does not introduce the sign. But if we do the integration over surfaces, keeping track of the orientation, then this will actually become much more essential. Our next topic will be more general surface integrals, where we will talk about orientation. And at that moment, this will become more clear. Right now, it looks a little strange that why we didn't care about it before, and now suddenly I care about it. Well, because we didn't have to explain it before, but now we have to. So that's roughly the answer. That's right. Well, the question is about line integrals. In the case of a line integral, right, we were supposed to take this vector field, df dx I plus df dyj, and we were supposed to take the dot of this with dr. When you take the dot with dr, you get this expression. I have explained now this expression as one obtained from f by this rule, by this procedure. The reason why I explained this is I wanted to show there is some uniformity between these two formulas. Without this explanation, these two formulas will completely disjoint. Right? In this case, I take this expression. In this case, I take this. It looks very arbitrary, very ad hoc. Right? So it looks like you have to simply memorize this expression. There's no other way to see, like, why is it dq dx? Why is it not dq dy minus dp dx, for example? Right? That's a natural issue, a natural question that arises here. What I try to explain is that actually this is not an arbitrary expression. This is an expression which can be obtained by some universal procedure. That procedure can also be used to explain the formula from last week. Right? So you don't have. This is something which is not in the book, and you don't have to memorize it. I think it's a good idea to memorize it because then if you not memorize it, to understand it, because then you don't have to memorize this formula. If you understand this procedure, this just falls out, as I have just explained. But you don't have to do it. This was just an explanation. I wanted to give you an intuitive explanation of what this formula is about and the connection between the two formulas. Okay? But if you like, you may just memorize these two formulas separately and not necessarily think of them as two special cases of something general. Yes.
So if pdx plus qdy is different from vector field,
Here, that's right. PDX. You can think of this as integral of vector field. That's right.
so what is just a bunch of lowercase f for the one-dimensional case, right?
Oh,